so as it turns out, there is one more variant of the amplifier that we just did, and let me lead with the reason for exploring a different variant. Then we can delve into it in more detail. Okay, so let's say I don't connect this, and I mean there will be some feedback stuff connected here, so that is regardless. So we were doing unity gain feedback, but it need not necessarily be the case. Your H can be 1 by 2, a closed loop can be 2 or 4 or 5, or there can be a whole bunch of stuff associated here. The part that I am trying to motivate here is what is the maximum voltage, but what is the maximum quiescent voltage that V0 can go? What is V0 max? V0 max will be equal to VO1 max minus 1 threshold voltage plus V overdrive, right? What is VO1 max? In this case, what is VO1 max? It is VDD minus 1 overdrive voltage. I am assuming all the overdrives and threshold voltages are identical. They not necessarily be the case, but at least they will be in the ballpark range, right? So VO1 max becomes VDD minus 1 V overdrive. This becomes minus threshold voltage minus V overdrive. So this is approximately 3 minus, this is let's say 0.5, and 2 overdrive is like 400. So 3 minus 0.9, that is 2.1 volt. Okay, did I make a mistake? Yeah, right, 2.1 volt. Okay. So what is the maximum this voltage can go to? Then this voltage can go to 2.1 volt. Okay, but now let's say I am operating with a lower supply voltage, because many technologies have a lower supply voltage. So let's say if VDD is let's say 1.8 volt, right? So then okay, and then what is VO max? VO max will be 0.9 volt, right? Okay, so what percentage of the possible signal swing is lost in the first case? So what I am essentially saying is that this voltage 0.9 by 3 volt, this ratio, right, or approximately 1 by 3, or rather I can simply say that approximately 30% of max possible swing is lost, or 33%, right? 33% of the max possible swing is lost due to biasing. So in the second case, how much? 50% of the, or rather not max possible swing, 33% of VDD is lost due to biasing, and that 50% of VDD is lost. And since your power is directly proportional to VDD, you can see that in the first case 33% of the power is lost just to keep this guy in saturation properly, right? In the second case 50% is lost, and you can see that this problem becomes increasingly more acute as the threshold voltage drops down, right? So that led to that coupled with another consideration has led to exploration of different architectures, right? So one possible scenario is this. one possible scenario is, so we have to put something here, and so there we have a feedback, right? So here we have to put a transistor. Here if we put a NMOS transistor and bias it as we did, right? The problem was, the major problem was this voltage was capped, and on top of that I am getting a VGS here, right? The major problem is we are getting a VGS drop between VO1 and VO, correct? So that is essentially a big problem. But what if I don't use a PMOS? What if I use an NMOS? Now you might say that we saw that using a PMOS, sorry, I mean what I meant, what if I don't use an NMOS, I use a PMOS? But you might say that we saw, like in the module 1, that using a PMOS is a problem because a common drain buffer is a problem, right? But what if we say that we will not use a common drain buffer, we'll use a second stage common source amplifier? What I am essentially saying is, what if we do this block diagrammatically? Let's say we have one amplifier and we cascade it with another amplifier, or rather let's say we cascade it with another amplifier and then drive an RL. Then what happens? Then you see that naturally it seems like I can get even more gain, because in this structure, in the structure that we have discussed till now, the current buffer, right? So the voltage buffer, the second stage, is not giving you any gain. In fact, its gain is slightly less than 1, if at all, right? The maximum gain that you can get between the gate and the source of a voltage buffer is 1, theoretically. In practice, you get less than 1. But if the second stage is also a gain stage, right? If the second stage is also a gain stage, then I can get some gain out of the second stage also. I mean, that seems to be an even better situation, isn't it? So we get more gain. But what about the headroom? So let's consider that. So in order to make this a common source amplifier, what should we do? We have to ensure that the source is grounded. For the second stage, the source becomes grounded, right? In this case, the drain is grounded, but in the second stage, source has to be grounded. Now, if we simply have to ground the source, we cannot use NMOS, we can use a PMOS. So let's use a PMOS. An incremental grounding is equivalent to saying it connects to VDD, right? So in principle, the second stage is a common source PMOS amplifier, right? And we put in negative feedback and all those things. And now let's consider the loop gain and everything. Okay, so before we consider loop gain, let's consider what is, so if let's say this is connected like this or through some negative feedback stuff, what is the maximum voltage V0 can go to? So what is the maximum voltage V01 can go to? V01 can go to, again, VDD minus 1V overdrive. What is the maximum voltage V0 can go to? Note that this is a drain. So drain of a PMOS transistor can go higher than 1 threshold voltage above the NMOS, above the gate, right? In principle, right? But I mean, in principle, what in this case, how if I consider the case of, if I only look at the gate and the drain, if we only, so for saturation of M5, all we need to ensure is that V0 is less than Vg of M5 plus threshold voltage, right? Which is VDD minus V overdrive plus threshold voltage, right? So in the cases that we took, it becomes VDD minus 0.2 volt plus 0.5 volt. So this is like VDD plus 0.3 volt. This is the saturation condition for M5, but you can readily see that V0 cannot go above VDD, right? Because if V0 goes above VDD, the quiescent current direction has to change, but that is not possible. So what is the maximum that V0 can go to? So this is not possible. This is impractical. So what is not possible? So what is the other? What is the maximum that V0 can go to? Then V0 basically can go to there the issue that you will have is if this guy goes to VDD minus V over drive, can you comment on the condition of M5? Is M5 on or off? Right? So what is the VSG of M5? The VSG of M5 is V over drive only, but it has to be threshold voltage plus V over drive, right? So if this is the condition, if VGM5 is equal to VDD minus V over drive, then M5 is off. So max, what is the max VG of M5? Max VG of M5 is VDD minus 1 VSG of M5. Now this is possible, this is not a problem, because this falls within the range of the allowable voltage swing at Vout1. So what is the max VO? So max VO is this plus threshold voltage, which means VDD minus 1 V over drive, right? So this is approximately VDD minus 0.2 volt. So in essence, in this case, V0 can go very close to VDD, right? Percentage wise, right? If with VDD is equal to 1.8 volt supply, on the higher side, only 0.2 volt is lost, right? So 0.2 by 1.8 is almost like 11%, right? So 11% power, approximately 11% power or VDD is lost due to biasing. So this is far better than the 50% loss that we were getting in the previous architecture, right? And that is why you will see that as the voltage supplies have lowered and lowered, people have gone away from using a common drain output stage, right, and have stuck to using the common source output stages. Okay, now the stuff that I didn't talk about till now is what is the gain of the common source output stage. So let's investigate that also. So loop gain, let's do loop gain, right? So to do loop gain, what do? We incrementally ground the input, break the loop, right? This loop will be closed, so I'm breaking it here, and I apply a test voltage here, and you observe the return voltage here, and we know that there is an output resistance R out here, right? Okay, so what is the loop gain? L, or rather let's find out what is V return. So what is Vout1? Vout1 is minus GM times V test times R out, right, or this is R out 1, right, and here we have this, right? Okay, so what is VO? What is VO? VO will be, okay, you will soon see a problem. So let me go ahead with this, then you will soon see a problem. So VO is what? VO is, now note that VO, this is a common source stage, so there is another inversion. So VO is minus GM5 times V out 1, right? So that should be small, right? So this is V out 1, this is VO. GM times V out 1 times RL parallel RDS 5, right? So this is almost equal to, if RL is, by definition RL is a very heavy load, right? So RDS has to be negligible. This becomes G minus GM5 P out 1 RL, which is equal to GM times R out 1 times GM5 times RL. So what is L? L is minus V return over, so this is by the way V return, right? Minus V return over V test, which is minus GM times GM5 times R out 1 times RL. So what does this minus sign tell you? What does this imply? This minus sign in the loop gain essentially implies that the loop is in positive feedback. Why is the loop in positive feedback? Why do you think the loop is in positive feedback? So that's easy to see. So let's say we excite, we increase that voltage, right? If we increase that voltage, what is going to happen to V out 1? What is going to happen to V out 1? V out 1 is going to decrease. What is going to happen to V naught? V naught is going to increase. So this voltage increases. So whatever excitation we fed, the same, I mean, return excitation in the same direction is getting fed back, which means this is a positive feedback loop, right? So what is the solution? We cannot connect the feedback at the negative terminal. We have to connect the feedback at the positive terminal, correct? So we have to connect the feedback at the positive terminal. And here we'll have this VCM plus VI or whatever. Okay. And then if we have to do a loop gain analysis, we short this, right? We short this and we apply a test voltage here. And we observe the return voltage here. So again, let's go around the loop. Let's see. So if this increases, what happens to V out 1? V out 1 increases. If V out 1 increases, what happens to V out? V out decreases. And now when the loop is closed, you can see that we have a negative feedback, negative voltage, that is, or rather a voltage in the negative direction that is coming back, which means that all these signs will change. This will become positive, this will become positive, this will become positive. Okay, so the loop gain becomes this. The loop gain becomes this. Now note that this loop gain is proportional to RL, but as long as you are keeping GM5 times RL to be at least unity or higher, then you have high loop gain. Now again, a quick reminder, I have to emphasize the fact that we are not looking for a precise value of loop gain. We are looking for a high enough value of loop gain. Why are we looking for a high enough value of loop gain? We are looking for a high enough value of this loop gain or the open loop gain so that we have a precise value in the closed loop gain, right? So this is important. So let me write this down. So we are looking for a high value of open loop gain so that we have a precise closed loop gain or closed loop, yeah. So we are not necessarily looking for a precise value of open loop gain. We are looking for a high value of open loop gain so that we have a precise value of closed loop gain. Why do we say so? because note that V naught over Vi is 1 over H 1 by 1 plus 1 by L. So as long as L is high enough, I can neglect 1 over L with respect to 1, and V naught over Vi will become 1 over H. We are looking for 1 over H, and since we know that H is a ratio of some things, that's, I mean, in the cases that we have seen, H is a ratio of resistors, we are good. Okay, fine. So now what we'll do is let's get rid of all these symbolic GMs and put the transistors back, right? So let me sketch this once, and let's see how the transistor equivalent of this circuit looks like. So what will be the transistor equivalent of this? So this GM, we know this is a single stage differential amplifier. We have done it multiple times. What is the second stage? This is Vout1. The second stage is a PMOS second stage, right? So this is I2, 2 not. Okay, so now where do you think should I connect the output? Should I connect the output here, or should I connect the output here? So let's connect the output here, and let's see whether our negative feedback is intact or not. So in the loop, somewhere in the loop, let's apply an excursion. So let's say this voltage increases. If this voltage increases, what happens to Vout1? Naturally, you see that there is an inversion, right? This is like a common source amplifier. If this voltage increases, Vout1 decreases. If Vout1 decreases, what happens to Vout, the final output? This voltage increases. So naturally, you see that this is a positive feedback loop, right? So we cannot connect the feedback at this terminal, which means we have to connect the feedback at the other terminal. And we'll have to connect the input here, right? This will be VCM plus Vi, and this will be Vout. This is a unity gain configuration of our buffer, right? Okay. So if we didn't want unity gain configuration, what would we have done? We had to again put a R by R or K minus 1 R and R ratio, and take the feedback part and feed it back, right? So that's what we had to do. We would have done, but in this case the configuration is that of unity gain, right? So if the configuration is that of a unity gain, what is the what is H? H by definition is what? H by definition is V naught over Vi, limiting value when L tends to infinity, right? So if L tends to infinity, that is the loop gain tends to infinity, right? What is going to happen? If the loop gain tends to infinity, clearly these two voltages will track each other, and Vout will be equal to Vi, right? Unity gain buffer. So H is 1. What is loop gain? Loop gain we know is, in this case, GM1 Rout1 GM5 times RL, correct? So what is incremental V naught over Vi? Incremental V naught over Vi is 1 over H 1 by 1 plus 1 by L, which is equal to, H is 1, so all it becomes is 1 plus 1 over GM1 Rout1 GM5, right? Okay, so note that this is again one order of magnitude better than if we had connected RL directly to the output of GM, right? Because the steady state error in this case is lowered by a factor of the gain of the second stage, right? So because the loop gain is higher by this factor, right? The loop gain is higher by a factor of GM5 times RL, hence the steady state error, the final error, would also go down. So the tracking of the output voltage with respect to the input, regardless of variation of some variation of RL or even some variation of process voltage temperature, will be much better in this case. Okay. Now before we end today's lecture, a natural question that comes is, the second stage could have been an NMOS second stage as well, right? I could have used an NMOS second stage as well, isn't it? So what I am essentially saying is, I could have as well used an NMOS common source amplifier in the second stage. In that case, this output would have had to come here, and we probably would have had to connect the current source here, right? And this probably would have been the VCM, and this guy goes and connects here, and all those things we would have had to do. But what's the issue? Now the issue is dependent upon what is the expected output voltages, what is the quiescent condition. But in general, as you see that this natural voltage of the output of the first stage is more towards VDD, right? And it's probably true that the natural voltage, the expected VGS of this M5 is more towards ground, right? So the range of acceptable voltages, the overlap of the range of acceptable voltages might not be sufficient to use as NMOS second stage. But having said that, if the VDD really comes down, if let's say VDD is like 1 volt, then it's quite possible that the range of the first stage, the range of acceptable quiescent voltages of V0, VO1, and the range of acceptable quiescent voltages for M5 VGS might be okay. So in that case, an NMOS M5 is also probably fine. Again, as I said, it depends upon what is the situation on the ground, what you are trying to design for. It's not necessary that just because I said that if you use a NMOS first stage, you have to use a PMOS second stage or the PMOS common source amplifier, need not necessarily be the case all the time, right? Okay, so as you can see that, if you remember at the beginning of the course, I had promised you a final architecture. As you can, if you look back at this architecture, this seems like it is almost similar to whatever we promised, right? We are getting closer and closer there. In the next few lectures, you will see a more in-depth analysis of what this is, whether this will work as is. Let me give you a brief primer. There are issues with this architecture with regards to stability, right? So if you just connect this like the way we have, there can be some interesting phenomena that can happen. We will discuss those things in the next few lectures, right? Okay, see you.